Here we have another related rate problem involving a rectangle whose dimensions are changing. And so we're told that the width is increasing at 4 centimeters per second and the length is decreasing at 3 centimeters per second. And we're asked to find out how the area is changing, or how fast the area is changing, when the width is 10 centimeters and the length is 15 centimeters. So, as usual, we're going to start by modeling this. We've got our rectangle here. And rectangle has 2 dimensions, so I guess I'll call this x and this y. And we are told, actually maybe we'll use L and W since it stands for length and width. So we'll call this the length and that the width. And so what do we know about this rectangle in terms of how it's changing? Well, we know that the width is increasing at 4 centimeters per second. So we'll say dw dt equals 4. And the length is decreasing at 3 centimeters per second. So you got to be careful here because it's decreasing, so I have to represent that as -3. If we put units in, we have that. And so what we want to know is we want the rate at which the area is changing with respect to time. We want dA dt when W equals 10 and L equals 15. Alright, so we know what we want. What we need now is an equation that relates the rate of change of the variable we're interested in, dA dt, with W and L. So we know that the area of a rectangle is just length times width. So A equals L times W. Now I need to take the derivative with respect to time. So the derivative of the area is going to be dA dt. And that's going to equal. Now the derivative of L times W, since L and W are both variables, and they're more specifically, they're functions of time. So they're 2 functions being multiplied. We need to use the product rule. So the product rule would say, let's take the derivative of L, dL dt, and you can think of it as 1 times dL dt, but it's just L to the 1. So dL dt, leave the W alone, plus leave the L alone. The derivative of W is 1 times dW dt. So now we've got our differential equation here. And we're going to obviously we're going to be able to solve for this, so we're going to substitute in dL dt. So dL dt is -3. At the instant we're interested in is when W is 10, so that's a 10. L is 15, and dW dt was a 4, and that will give us our dA dt. So I should have put in as our step to be thorough. This is the sub and solve step. Alright, and so we get -30, so dA dt is equal to -30 plus 60, which gives you 30. Now the units on this are going to be centimeters squared per second, because that's the rate of change of area. Alright, and so then we can interpret, and we can say the area is increasing at a rate of 30 square centimeters per second at this instant.